The quiz problem was involved an object which runs down a ramp for a specified distance, actually a specified change in its altitude on the ramp, and then goes off the end of the ramp and falls as a projectile to the floor, a distance delta h lower. In this case, delta h is 1 meter. Since the horizontal velocity remains constant, we see that delta x is going to be v naught delta t. This is the first thing we have to do to determine the requested results on the quiz. Now, the quiz actually asks now for a 1 centimeter fall on the ramp. Then, how fast will the object be going, and how far will it travel? I think actually the quiz just asked how far it would travel, but we should see that we need to determine first how fast it's going. So for a 1 centimeter fall, our potential energy change is going to be whatever the mass of the object is, times 980 centimeters per second squared times negative 1 centimeter. Now, assuming, as instructed on the quiz, that the change in kinetic energy is, I think the way it was stated in the quiz was that the gain in kinetic energy is equal to the loss of potential energy, or that all the potential energy loss goes into kinetic energy, and also that the object starts from rest. If the object starts from rest, its change in kinetic energy, of course, will be 1/2 mv squared, and that's going to be the negative of the change in potential energy. Well, the change in potential energy is, of course, negative as the ball goes down the ramp, and we set 1/2 mv squared equal to that negative of that potential energy. And actually, I think I left off a negative sign here. There should be a negative out in front here. Let's see if I can put that in. This is a little bit of an awkward angle. That was good. The background slipped, but this is supposed to be a minus sign in front of the M. So we have negative of the change in potential energy. Negative, the negative change is of course going to be positive. And then our 1/2 mv squared set equal to that. We can easily solve for v. And for the 1 centimeter fall, we obtain 44 centimeters per second. Now what we want to do is we want to find the total horizontal range for each fall. And we have falls of 1, 4, and 16 centimeters. We find that for each of these falls, if all the potential energy change goes into kinetic, and if that energy results in an initial velocity that's completely horizontal, no vertical component, the ball coming off the edge of the ramp at a horizontal, that we get these initial velocities by the same method that I used before. Now, recall that delta H was taken to be 1 meter, and we're going to be able to calculate delta X from V naught if we know delta T, just by the simple idea that the horizontal velocity remains constant. Well, if we fall from rest, and vertically we're falling from rest, okay? Let's look back here for a minute. Sorry to jerk you around, but vertically there's no velocity here, and the ball is simply falling from rest, and its vertical motion is simply that fall. If we fall 1 meter from rest, then we have an acceleration of negative 9.8 meters per second squared, or 9.8 meters per second squared, depending on which direction you want to be positive. And we can easily use the kinematic equations to find that delta T is 0.44 seconds. Then, if V naught is 0.44 centimeters per second, as it is for the 1 centimeter fall, acceleration in the x direction, in the direction of this motion, is 0. We're going to get delta S V naught delta T plus 1/2 A delta T squared, and we easily solve to find that delta S is 20 centimeters. The fact that that A is 0 means that we're just going to multiply V naught times T to get our delta S, and of course we'll do the same thing for the other two initial velocities.